This time, what's wrong with Kirchhoff's voltage law? Well, first a reminder of what Kirchhoff's voltage law says. Kirchhoff's voltage law says that the sum of the voltage differences across the components around a closed loop is 0. Therefore, if we built a circuit like this, with a resistor here, and connected the two ends of the resistors with a wire, there would be no voltage across the resistor because a wire with 0 resistance would have the same voltage at both ends. V1 would have to be equal to V0, and therefore no current would flow through this resistor. Right, watch this. This is an excerpt from a video made by Professor Melloch from Purdue University. That is a coil of wire. It's a very long coil of wire. There's multiple turns in it, but it is still just a coil of wire with a very, very small and negligible resistance. The ends of the wire are connected to this ammeter here. Now, this ammeter has a resistance, possibly around 100 ohms or so. And if a current is detected flowing through the ammeter, the needle will move. Remember, both ends of the ammeter are connected together just through a wire of negligible resistance. Therefore, the voltage on both terminals of the ammeter must be the same. Therefore, no current can flow through the ammeter. Oh dear. What he's doing is moving a magnet through that coil of wire. And when the magnet moves, the ammeter registers a current. Now that turns out to be a big problem for Kirchhoff's voltage law. We have a circuit like this with the resistance here, and the ends of the resistor are connected together with a wire. And if there is a varying magnetic field through the circuit, through this loop of wire here, then a current flows through that resistor and would be detected by an ammeter. But if a current is flowing through a resistor, then the voltage at this point here, V1, must be bigger than the voltage at this point here, V0. But they can't be, because they're connected together by a wire. Even if you assume that the wire does not have a negligible resistance, but does have a certain small resistance, then we've still got a problem, because if the current is flowing this way through this resistor, then V1 must be bigger than V0. If V1 is bigger than V0, then we should have a current flowing through this resistor as well in this direction. But this now violates Kirchhoff's current law, because if you look at this node at the top of the circuit here, we have two currents flowing out of this node, but no current flowing in. Something is wrong. This turns out to be quite a serious problem for Kirchhoff's voltage law. If you have a varying magnetic field flowing through your circuit, then Kirchhoff's voltage law just doesn't work. In fact, the whole concept of voltage doesn't really work either. Again, this doesn't cause too many problems in practice for most circuits, because the effect is quite small. In order to see the effect on the ammeter in the video, Professor Melloch had to use a very large number of turns of wire. And the more turns of wire you have here, the greater the effect. With only a single turn, such as you might have if you just built the circuit with a single wire going from here to here directly, then the effect would be much, much smaller and is usually negligible. It never goes away though. You'll always have a small amount of changing magnetic field through a circuit, possibly the stray magnetic fields produced by transformers, or just the magnetic fields which are part of electromagnetic radiation, light and radio waves. There will always be some changing magnetic field through a circuit, and that means that Kirchhoff's voltage law never works perfectly. But the error is often so small that we can neglect it. Just remember to be careful if you're applying Kirchhoff's voltage law to a circuit in which there is a large magnetic field which is changing. Next time, we'll look at Kirchhoff's current law and see what's wrong with that one.